Okay. Just getting stuff set up here. Sorry, y'all. What up? Really? It's been that long, huh? It's not even my recents. Dang. All right. Here we go. Chapter 7. All right. Sweet. Hello, everybody. Welcome back into the stream today. Hope you're having a wonderful day. I appreciate you guys so much for joining me, and thanks so much. So today we're gonna be back in. Well, I've got to actually start my recording too. So hold on one sec, you guys. We have a lot of white space here, so I can drag this over. Oh. Like there. Just a little bit bigger. Maybe we'll zoom in. Okay, cool. Thanks so much for being here. Let's go ahead and start the recording. My kitty is making some noise. Hold on, I got a hot pie. Got a pot pie in the oven, so let me go check on that real quick, and we'll get started on the reading. So give me 1 second. Okay, we got a couple more minutes on that, so we can get started here. All right, let me go ahead and start my recording for the playback, and we'll go ahead and get going here. 1 second here. Go to chat. Okay, let me see here. I think that made chat transparent. Someone give me a chat here. Okay, cool. All right, nice. Look at that. That's awesome. Hey, Sullivan, how's it going? All right, guys, let's get going here. I started the recording. Let me do my little intro. Bear with me on the cringe. All right, everyone. All right, hello, everybody. Welcome back to the channel. My name is Michael, and I hope you're having a wonderful day so far. Today, we're going to be jumping back into C Programming, A Modern Approach, second edition by K.N. King. We're going to be jumping into Chapter 7, Basic Types. So super excited to get started on this one and get some more information on, giving our variables some type definitions. Cool. Chapter 7, Basic Types. Make no mistake about it. Well, hold on. This is the live stream. This is from the live stream where I read the... This is from... Oh my gosh. Oh god. This is from the live stream where I read the entire chapter live. If you'd like to join me, I stream myself learning computer science and programming almost every single day. Thanks so much for being here. Let's go ahead and get started. Okay, that's fine. Whatever. God. Okay. Chapter 7. Basic types. Make no mistake about it, computers process numbers, not symbols. We measure our understanding and control by the extent to which we can arithmetize an activity. So far, we've used only two of C's basic built-in types, int and float. We've also seen underscore bool, which is a basic type in C99. This chapter describes the rest of the basic types and discusses important issues about types in general. Section 7.1 reveals the full range of integer types, which include long integers, short integers, and unsigned integers. Section 7.2 introduces the double and long double types, which provides a larger range of values and greater precision than float. Section 7.3 covers the char type, which we'll need in order to work with character data. Section 7.4 tackles the thorny topic of converting a value of one type to one. Section 7.4 tackles the thorny topic of converting a value of one type to an equivalent value of another. Section 7.5 shows how to use typedef to define new type names. Finally, Section 7.6 describes the size of operator, which measures the amount of storage required for a type. 7.1 Integer types. Right. C supports two fundamental different kinds of numeric data, integer types and floating types. Values of an integer type are whole numbers, while values of floating type can have a fractional part as well. The integer type, in turn, are divided into two categories, signed and unsigned. Signed and unsigned integers. The leftmost bit of a signed integer, known as the sign bit, is 0 if the number is positive, or 0, 1 if it's negative. Thus, the largest 16-bit integer that has a binary representation, 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, which has the value of this, the largest 32-bit integer is this, which has a value of this. An integer with no sign bit, the leftmost bit is considered part of the number's magnitude, is said to be unsigned. The largest 16-bit unsigned integer is this, and the largest 32-bit unsigned integer is this. By default, an integer variable are signed in C. The leftmost bit is reserved for the sign. To tell the compiler that a variable has no sign bit, we declare it to be unsigned. Unsigned numbers are primarily useful for system programming and low-level machine-dependent applications. We'll discuss typical applications for unsigned numbers in Chapter 20. Until then, we'll generally avoid them. C's integer types come into different sizes. The int type is usually 32 bits, but maybe 16 bits on older CPUs. Since some programs require numbers that are too large to store in int form, C also provides long integers. At times, we may need to conserve memory by instructing the compiler to store a number in less space than normal. Such a number would be called a short integer. To construct an integer type that exactly meets our needs, we can specify that a variable is long or short, signed or unsigned. We can even combine specifiers like long, unsigned, int. However, only the following 6 combinations actually produce different types: short int, unsigned short int, unsigned int, long int, unsigned long int. Hold on, let me go turn off the oven. Set timer for 12 minutes.
12 minutes?
We'll let that cool down. Other combinations are synonyms for one of these 6 types. For example, long signed int is the same as long int, since integers are always signed unless otherwise specified. Incidentally, the order of the specifiers doesn't matter. Unsigned short int is the same as short unsigned int. C allows us to abbreviate the names of integer types by dropping the word int, for example. Unsigned short int may be abbreviated to unsigned short, and long int may be abbreviated to just long. Omitting int is a widespread practice among C programmers, and some newer C-based languages, including Java, actually require the programmer to write short or long rather than short int or long int. For these reasons, I'll often omit the word int when it's not strictly necessary. The range of values represented by each of the 6 integer types varies from one machine to another. However, there are a couple of rules that all compilers must obey. First, the C standard requires that short int, and long int each cover a certain minimum range of values. See section 23.2 for details. Second, the standard requires that int not be shorter than short int and long int not be shorter than int. However, it's possible that short int represents the same range of values as int. Also, int may have the same range as a long int. Table 7.1 shows the usual range of values for the integer types on a 16-bit machine. Note that short int and int have identical ranges. Cool, so this table 7.1 has short int with negative 32,768 up to 32,767. Unsigned obviously means positive, so these go, and these are in the short, so 0 to 65,000 for short, for unsigned shorts. Int, has similar values to just short int, right? Or a similar range of value. Unsigned int has similar values to unsigned short int. Long int is negative 2 billion to 2 billion. And the unsigned long int is 0 to 4 billion. About. Headphones are dying. Let me plug them in. Hold on a minute. 1 sec. Table 7.2 shows the usual ranges on a 32-bit machine. Here, int and long int have identical ranges. So this is for a 16-bit above in 7.1. 7.2 has this is for a 32-bit machine. So short int on both are the same. Unsigned short int are the same on both. Int, however, is a lot larger because you have obviously double the amount of bits to use to make numbers up. Unsigned integers, they can go up to that 4 billion cap as well. Gotcha. In recent years, 64-bit CPUs have become more common. Table 7.3 shows typical ranges for the integer types on a 64-bit machine, especially under Unix. So as you can see, it just gets a lot bigger of the numbers that we can hold in memory with these bits and bytes. Once more, let me emphasize that the range shown in Table 7.1, 7.2, and 7.3 aren't mandated by the C standard and may vary from one compiler to another. One way to determine the ranges of the integer types from a particular implementation is to check the limits.h header, which is part of the standard library. This header defines macros that represent the smallest and largest values of each integer type. Integer types in C99. C99 provides 2 additional standard types, long int and unsigned long int. These types were added because of the growing need for very large integers and the ability for newer processors to support 64-bit arithmetic. Both long types are required to be at least 64 bits wide, so the range of long int values is typically negative 2 to the power of 63, or this very large negative number. 2 to the power of 63 minus 1, or this very large unsigned number. And a range of unsigned long int values is usually from 0 to 2 to the power of 64 minus 1, this even larger unsigned int value. The short int, long int, and long int types, along with the unsigned char type, are called standard signed integer types in C99. The unsigned short int, unsigned long int, and unsigned long int types, along with the unsigned char type and the underscore bool type, are called standard unsigned integer types. In addition to the standard integer types, the C99 standard allows for implementation defined extended integer types, both signed and unsigned. For example, a compiler might provide signed and unsigned 128-bit integer types. Integer constants. Let's turn our attention to constants, numbers that appear in the text of a program, not numbers that are read, written, or computed. C allows integer constants to be written in decimals base 10, octal base 8, or hexadecimal base 16. Octal and hexadecimal numbers. An octal number is written using only the digits 0 through 7. Each position in an octal number represents to a power of 8, just as each position in a decimal number represents to a power of 10. Thus, the octal number 237 represents the decimal number 2 times 8 to the power of 2 plus 3 times 8 to the power of 1 plus 7 times 8 to the power of 0, which is equal to 159. A hexadecimal or hex number is written using the digits 0 through 9 plus the letters A through F, which stands for 10 through 15 respectively. Each position in a hex number represents a power of 16. The hex number 1AF has a decimal value 1 times 16 squared plus 10 times 16 to the power of 1 plus 15 times 16 to the power of 0, which is equal to 431. Decimal constants contain digits between 0 and 9, but must not begin with a 0. Octal constants contain only digits between 0 and 7 and must begin with a 0. Hexadecimal constants contain digits between 0 and 9 and letters between A and F, and always begin with 0x. The letters in a hexadecimal constant may be either uppercase or lowercase. Keep in mind that octal and hexadecimals are nothing more than an alternative way of writing numbers. They have no effect on how the numbers are actually stored. Integers are always stored in binary regardless of what notation we've used to express them. We can switch from one notation to another at any time and even mix them. 10 plus 015 plus 0x20 has a value of 55 in decimal. Octal and hex are most convenient for writing low-level programs. We won't use these notations much until chapter 20. The type of a decimal integer constant is normally int. However, if the value of the constant is too large to store it as an int, the constant has a type long int instead. In the unlikely case that the constant is too large to store as a long int, the compiler will try unsigned long int as a last resort. The rules for determining the type of an octal or hexadecimal constant are slightly different. The compiler will go through the types int, unsigned int, long int, and unsigned long int until it finds a more capable type of representing the constant. To force the compiler to treat a constant as a long integer, just follow it with either To force the compiler to treat a constant as a long integer, just follow it with the letter capital L or lowercase l. Or capital or like L, right? To indicate that a constant is unsigned, put the letter U, capital U, or U after it, right? So that you can make things long integer types within hexadecimals by specifying a capital L at the end. And you can make them unsigned by specifying a capital U. Capital L and U may be used in combination to show that a constant is both long and unsigned. So this number is both a long number and unsigned. So it's a positive large number. The order of the L and U doesn't matter, nor does their case. Oh, got you. Case does not matter. Integer constants in C99. In C99, integer constants that end with either LL or LL, the case of the two letters must match, have type long int. Adding the letter U or U before or after the double L's denote a constant of type unsigned long int. C99's general rule for determining the type of an integer constant are a bit different from those in C89. The type of a decimal constant with no suffix, capital U, lowercase u, capital L, lowercase l, double capital L, or double lowercase l, is the smallest of the types int, or long int that can be represent the value of the constant. For an octal or hexadecimal constant, however, the list of possible types is int, unsigned long int, long int, and unsigned long int, in that order. Any suffix at the end of the constant changes the list of possible types. For example, a constant that ends with the capital U or lowercase u for unsigned must have one of the types unsigned, int, unsigned long int, or unsigned long int. A decimal constant that ends with the capital L or lowercase l must have one of the types long int or long int. There's also a provision for a constant to have an extended integer type if it's too large to represent it using one of the standard integer types. Integer overflow. When arithmetic operations are performed on integers, it's possible that the result will be too large to represent. For example, when an arithmetic operation is performed on two int values, the result must be able to be represented as an int. If the result can't be expressed as an int because it requires too many bits, we say that overflow has occurred. The behavior when integer overflow occurs depends on when the operand were signed or unsigned. The behavior when integer overflow occurs depends on whether the operands were signed or unsigned. When overflow occurs during an operation on signed integers, the program behavior is undefined. Recall that section 4.4 that the consequences of undefined behavior may vary. Most likely the result of the operation will simply be wrong, and the program could crash or exhibit undesirable behavior. When overflow occurs during an operation on unsigned or positive values, we'll finish up this page and grab my pot pie. We don't want it to get cold now. Recall from section 4, When overflow occurs during an operation on unsigned integers, positive values, though the result is defined, we get the correct answer modulo 2 to the power of n, where n is the number of bits used to store the result. For example, if we add 1 to the unsigned 16-bit number 65,535, the result is guaranteed to be 0. Because we went overflow of the int boundary. Reading and writing integers. Suppose that program isn't working because one of its int variables is overflowing. Our first thought is to change the type of the variable from int to long int, but we're not done yet. We need to see how the changes will affect the rest of the program. In particular, we must check whether the variable is used in a call to printf or scanf. If so, the format string in the call will also need to be changed, since the %d conversion only works for the int type. Reading and writing unsigned short and long integers require several new conversion specifiers. When reading or writing an unsigned integer, use the letter U, O, or X instead of the D in the conversion specification. If the U specifier is present for unsigned integer, the number is read or written in decimal notation, O indicates octal notation, and X indicates hexadecimal notation. So if we have a variable U, which is an unsigned int, which is a positive integer, we read U in base 10, we can use the %u specifier. Conveniently, it's the same character as the variable definition, which is kind of annoying, but we can use the %u specifier here to write in base 10. Is that by convenience or is that by design? Looks like it might be just by convenience to kind of show that it's a base 10 value. Now you can read it in base 8 and then print it out in base 8. And same with base 16 with this x. So you can read it in as the value and save it into u. Okay, got you. When reading or writing a short integer, put the letter h in front of d, o, u, or x. Short s, scanf, %hd, %s. Printf, %hd, s. So when we're doing a short integer, we put an h in front of the conversion specifier. When reading or writing long integers, put the lowercase letter l in front of d, o, u, or x, whichever type of integer, whether it be hexadecimal, octal, or base 10 you're using. So they're defining a long variable L here, which is a type long. They're going to save at the variable type in the variable long address the scanf for the long integer specifier here, and then print out the long integer specifier for the L variable. When reading or writing a long integer, C99 only, put the letters double L, lowercase, in front of D, O, U, or X. So long, double L, for a double L is our variable definition or name. We're going to scanf the double LD, so the long decimal or like integer, into the long variable. And we're going to print that out. Okay, then we have a program here, summing a series of numbers revisited. In section 6.1, we wrote a program that sums a series of integers entered by the user. One problem with this program is that the sum, or one of the input numbers, might exceed the largest value of an int variable. Here's what might happen if the program is run on a machine whose integers are 16 bits long. This program sums a series of integers. Enter integers 0 to terminate. 10,000, 20,000, 30,000, 0. The sum is -5536. The sum was 60,000, which wouldn't fit in an int variable, so overflow occurred. When overflow occurs with signed numbers, the outcome is undefined. In this case, we got an apparently meaningless number. When overflow occurs with signed numbers, what is signed here? We're summing a series of numbers. That are all positive, 10,000, 20,000, and 30,000. And we terminate on 0. To improve the program, let's switch to the long variable. Sums a series of numbers using long variables. We include the standard I/O. We have int main void. We have a long n variable and sum 0. We make the prompt that we're going to print a series of numbers, and we're going to enter until we hit 0. We're going to run a while loop and scan in the input that they say within the while loop and add that to the sum variable. Once the loop terminates, when n becomes 0, we actually print out what the sum is. The change was fairly simple. We declared n and sum to be long variables instead of int variables, and then in our printf we had to specify the long int specifier in the scanf and printf instead of just the %d. And cool, that brings us to 7.2, which is floating types. So let me go grab my pot pie, and I'll be right back. Hold on 1 second, guys. Want to check out. get some water. Let me refill my water here. All right, we got our water. We got our pot pie dinner here. Thanks for the patience, everybody. Now subscribe and make sure you subscribe. We're almost to 4,000 here. Hopefully we can hit it soon. All right. Ooh, steaming. Okay, that's got to cool down a little bit. Steaming. Okay. So let's go back through really quick and take some notes here. Okay, so we talked about int and float and bool, and then we talk about these other ones. So integer types and floating point numbers, values of integer types are whole numbers, while values of floats can have fractions. You have signed and unsigned integers, right? So signed integer. The leftmost bit of a signed integer, known as the sign bit, is 0. So we'll say the sign bit first. The leftmost bit in an integer which determines the sign, positive / negative of the number. The largest 16-bit integer has binary representation of this, which has value of this. So, okay, cool. So then we'll say 0 for positive, unsigned integers, 1 for negative signed integers. Okay. Then it gives us an example here. Great. Declare to be unsigned. So signed and unsigned. These integer types come in different sizes. Int is usually 32 bits, but maybe 16 bits for older CPUs. The programs require numbers that are too large to store in int form, so he also provides long integers. So then we have long integers, right? Numbers that are too large to be stored in an int variable. Right. Then we also have short integers, which are numbers that are too small to be stored in No. So it's not too small, right? It's just so we can save memory. If the number is small enough, we can save memory by using short variable declaration. To construct integer types exactly meet our needs, we specify the variables long or short, signed or unsigned. We can combine them. So you can combine both combine signed / unsigned with long / short to give greater specification on of variable definition. Variable / integer. Right. So we'll take these. Cool. So you can have like long integers, you can have short integers, signed integers, long signed, so short integers, unsigned short integers, short unsigned. You can make them either switch up the order or whatever, or you can omit the int altogether to, whatever. And then in this section, we talked about how the range values of processors, right? So CPUs and we'll say different CPUs process different size integers. And we'll do this. Let's take this in here. So this is going to be for 16-bit machine. So on a 16-bit system, right, where it's going to be this guy. On a 32-bit machine, it's going to be this guy here, where our longer integers get bigger, right? And then on a 64-bit machine, right, now we just have some very, very big numbers. Cool. So then we'll say limits .h is a header file that is a part of the standard library that which defines macros that represent the smallest and largest values of each integer type. Cool. C99 provides two additional types, long. So we'll say more types in C99. We'll say like you have long long, which can be signed or unsigned. And is used primarily to support 64-bit machines and their capability of using very large numbers. It's typically between this range and this range, as we talked about above. Okay. And then int values of this one. The short int types along with the unsigned char type are standard C. Okay. So standard signed integer types are the following. Unsigned short int, int, long int, and long int. Short int, long int, long int. And then we had also just int. Cool. And then we had in C99 the unsigned. Then we had these next ones these are called standard unsigned integer types in C99, right? Which are going to be the unsigned short int, unsigned int, right, this is just unsigned. Okay. Along with the unsigned char type and the bool type. So this also with the unsigned char type. Which we'll get to later. And then the underscore bool. Right. In addition to standard type, C99 allows for implementation of extended integer types, both signed and unsigned, for example. Okay, so extended integer types allowed in C99 allowed C99 for example 128-bit. Chill Quark. Hey man, I want to thank you. A couple weeks ago I started with the book and I'm currently in the projects of chapter 5. Nice, dude. Awesome. Yeah, you're grinding along with me. That sounds awesome, dude. Thanks for coming in today. Where are the job apps? Denied, dude. Left and right. Let me tell you. I did like a big session after we did that resume update. Threw out probably like, I'd say 20 to 40. Just, it's a break walls, dude. I don't know, man. I think we should just go work at Costco and like just live a chill, like honestly, like maybe just take it easier and learn the code and head up to Costco. Become a manager at Costco. That might be what we do. Okay. I'm gonna keep rolling here. Integer constants. Let's turn our attention to constants. Numbers that appear in the text or programs, not numbers that are read, written, or aloud. Text or program, not numbers that are read, written, or computed. Okay, so then we have constants, integer constants, which are numbers that are computed. Right? And C allows for, I'm going to take this right out of the book. Right out of the book. You're written in base 10, octal base 8, and base 16. So then we'll just do a quick note here for octal numbers. Right? Written using only 0 through 7, where each position is an octal, each position in an octal number represents a power of 8. Right, so 237 is actually 2 to the power of 8. You have to times 8, no, times 8 to the power of 2. Right, this position is 8 to the power of 0 times whatever's there. Right, so it's just going to be the number, basically, right? Okay. Whereas hexadecimal come on. Hex number is written using only 0 through 9 plus the letters A through F, which stand through 10 through 15 respectively. Each position in a number represents the power of 16. The hex number 1AF has the decimal value of this. Each position in a hex number represents a power of 16. Okay, gotcha. So that you just use the letters rather than using double-digit numbers, right? So to keep everything single digit, they switch over to letters once we exhaust 0 through 9. Okay, that makes sense. So we have decimal constants contain digits between 0 to 9 must not begin with 0. So we'll say octal constants must begin with a 0. We'll take an example here. Well, I don't need to take a picture of this. What am I doing? Zero 1 7 0 3 7 7 0 7 like that. Well, just do 1 because that kind of makes it look like it's like a 1 number or something, but it's not. Hexadecimal. So this must begin with a 0x. Come on. So example would be 0x7fff. We can do like capital, right? Lowercase. Okay. Keep in mind that octal has nothing more than alternatives. The type of decimal integer constant is normally an int. Right? Cool. So if you want to give types to your hexadecimals, you can specify long integers at the end of your hexadecimals with this L, right? So hexadecimals will say as well. Postfix L or L to the end to make the compiler read as a long integer. And then you can postfix capital U or lowercase u to the end to make the compiler read as a unsigned, right, or positive. Okay. We'll say both L and U can be used in combination and in any order. If the cool. C99 LL or double, okay, right? So we have in C99 LL or LL have type long int and right, cool. The type of a decimal constant with no suffix is the smallest of the types that can be represented of the value of the constant. For example, for an octal or hexadecimal constant, however, the list of the types are int, unsigned int, long int, unsigned long int, long int, unsigned long int, unsigned long in that order. A decimal constant that ends with L must have types long int or long int. Okay, cool. Let's talk about int. Let's just make some notes on integer overflow. Right? So when arithmetic operations are performed on integers, it's possible for the result to become too large to represent. when the result of arithmetic operations becomes too large for the initial variable type. For example, if you add two ints and it becomes too large, you can represent it as too many bits. We call it overflow. The behavior when integer overflows depends on whether operands were signed or unsigned. So we'll say signed on signed integers, program behavior is undefined. Signed overflow on signed integers causes undefined behavior. And we'll say overflow on unsigned integers the result is defined, but I don't really get this part. To the power of n. Bits used to store the result. So whatever number of bits was used to store the result, we take 2 to the power of that value and give it back in negative for unsigned. No, sorry, for positive. Were you doing pi like a month ago? Yeah, so what? What's up, bro? Hey, no one. How's it going? So constants is a fancy word for hard-coded values in your code. Kind of confusing me. Yeah, their wording on that one was a little bit confusing. So I think they're like constant. Yeah, define. And then there's constant variables, which I got a little confused on that too. I don't know. Whoops. All right. Shrouded Data. Just want to drop by. You say you inspired me. I plan to start streaming my studies as well. Nice, dude. Drop a link in the Discord or something. Okay, let's keep rolling. Okay, hold on. Let's finish up these notes here. Oh, there's so many notes. This is a long section. So when writing integers. So when reading or writing. Okay, so. So we'll go up to our. Okay, so we need to add in additional conversion specified. Okay. We have U, O, and X instead of the D. Wait, okay, so U is specifier, which represents the number read and written in decimal notation. Unsigned integer. Okay, so this is for unsigned, right? U, O, and X, which represents decimal of base 10. This is O is octal. Then X is hexadecimal. Cool. Which is base 16. So then we'll do, for short, integers. We're going to do H. D O U R. Come on. Okay. So then we have long integers, which is going to be a L in front of. Then you have long integers, which is just LL, right? Cool. And then this gives us the example. Nice, that caught us up here. That was 7.1. Let's do 7.2. Okay, and then this is 7.1. Just something we'll come back and get. Okay, let's keep it pushing. Cool. Let's keep it pushing. 7.2, floating types. The integer types aren't suitable for all applications. Sometimes we'll need variables that can store numbers with digits after the decimal point, or numbers that are exceedingly large or small. Numbers like these are stored in floating point format, so called because the decimal point floats. C provides three floating types corresponding to different floating point formats: float, single precision float; double precision floating point; and long double, extended precision floating point. Float is suitable when the amount of the precision isn't critical, calculating temperatures to 1 decimal point, for example. Double provides greater precision, enough for most programs. Long double, which supplies the ultimate in precision, is rarely used. The C standard doesn't state how much precision the float, double, and long double type provide, since different computers may store floating point numbers in different ways. Most modern computers follow the specifications in IEEE standard 754, also known as IEC 60559, so we'll just use it as an example. The IEEE floating point standard. IEEE standard 754, developed by the Institute of Electrical and Electronics Engineers, provides two primary formats for floating point numbers: single precision 32-bit and double precision 64-bit. Numbers are stored in a form of scientific notation, with each number having three parts: a sign, an exponent, and a fraction. The number of these bits reversed for the exponent determines how large or small numbers can be, while the number of bits in the fraction determines the precision. In single precision format, the exponent is 8 bits long, while the fraction occupies 23 bits. As a result, a single precision has a maximum value of approximately 3.4 times 10 to the power of 38, with a precision of about 6 decimal digits. The IEEE standard also describes two other formats, single extended precision and double extended precision. The standard doesn't specify the number of bits in these formats, although it requires that the single extended type occupy at least 43 bits and the double extended type at least 79 bits. For more information about the IEEE standard and floating point arithmetic in general, see Why Every Computer Scientist Should Know About Floating Point Arithmetic by David Goldberg back in March of 91. Table 7.4 shows the characteristics of the floating types when implemented according to the IEEE standard. The table shows the smallest positive normalized values. Subnormal numbers can be smaller. The long double type isn't shown in the table since its length varies from one machine to another, with 80 bits and 128 bits being the most common sizes. So for float, we have 1.17 times 10 to the power of negative 38 for the smallest, and the largest being 3.4 times 10 to the 38, with 6 digits of precision. And with a double float, we have 2.22507 times 10 to the power of 300 and negative 308. And for the largest value, we have 1.79769 times 10 to the power of 308 with 15 digits of precision. On computers that don't follow the IEEE standard, Table 7.4 won't be valid. In fact, some machines, float may have the same set of values as double, or double may have the same values as long double. Macros that define the characteristics of the floating types can be found in float.h header. In C99, the floating types are divided into two categories, the float double and long double. In C99, the floating types are divided into two categories. The float, double, and long double types fall into one category called the real floating types. Floating types also include the complex types, float underscore complex, double underscore complex, and long double underscore complex, which are new in C99. Floating constants. Floating constants can be written in a variety of ways. The following constant, for example, are a valid way of writing the number 57.0, 57.0, 57 point, 57.0E0, 57 capital E0, 57 5.7 E1, 5.7 E plus 1, 0.57 E2, 570.E negative 1. As you can see, there's many different ways to write the number with exponential, scientific form, and decimal form. A floating constant must contain a decimal point or a floating constant must contain a decimal point and or an exponent. The exponent indicates the power of 10 by which the number is to be scaled. If an exponent is present, it must be preceded by the letter capital E or lowercase e, and an optional plus or minus sign may appear after the capital E or lowercase e. By default, floating constants are stored as double precision numbers. In other words, when a C compiler finds the constant 57.0 in a program, it arranges for the number to be stored in memory in the same format as double variable. This rule generally causes no problem since double values are converted automatically to float when necessary. On occasion, it may be necessary to force the compiler to store a floating constant in float or a long double format. To indicate that only single precision is desired, put the letter capital F or lowercase f at the end of the constant. For example, 57.0 capital F to indicate that the constant should be stored in long double format, put the letter capital L or lowercase l at the end. 57.0 L. C99 has a provision for writing floating constants in hexadecimal. Such a constant begins with 0x or 0 capital X. Like a hexadecimal integer constant, this feature is rarely used. Reading and writing floating point numbers. As we've discussed, the conversion specifications %E, %F, and %G are used for reading and writing single precision floating point numbers. Values of type double and long double require slightly different conversions. When reading a value of type double, put the letter L in front of E, F, or G. double D, pause. Tim, chill. I know you heard that. So you have double with the variable D, scan F, where we're going to read into the variable D a long float. Sorry, we're going to read into the value of D a double float indicated by LF in this conversion specifier. Note, use L only in a scanf format string, not a printf string. In a printf format string, the E, F, and G conversions can be used to write either float or double values. C99 legalizes the use of L, E, LF, and LG in calls to printf, although the L has no effect. When reading or writing a value of type long double, put the letter capital L in front of the E, F, or G. So if you're reading long double for float values, right, you would use capital L in front of the conversion specifier. Okay. This is 7.3. Oh yeah, it's long. Holy cow. This one's long, boys. Pause. I think we might have to, I think I might pause it here. I was up really late last night coding again. I can't stop. Dude, once I get going in like a React flow, like it's really, you get in this kind of state where you just keep going and going and going and time just goes, man. You guys ever had that happen, yo? Where you're programming and time just starts like moving? Like I coded from, I didn't stream last night. Like I kind of just wanted to just like go without any pressure, like of people watching. Like I just wanted to just grind. And so I sat in my chair, in this chair from I think like 6:30 until I think midnight, just working on my new project. Okay. So I'm gonna stop my recording here and we'll come back and we'll pick up on 7.3. So let me stop the recording here. Beautiful. Cool. So we'll have to break this one up because this chapter is pretty long and I know that character types is going to get pretty dense here. Character types for sure is going to it's going to be a lot. So we'll let's just push what we got so far. We'll say start chapter 7. Hey Dublin, how's it going? I appreciate you so much for joining me and leaving me a comment. You're awesome, okay? Welcome. I have some project in mind. Do you have some project in mind that makes use of C? Yeah, I'm hoping to get more like familiar with just like hardware stuff and see if we can maybe like get like a microcontroller and like wire up maybe some like fans and like a light and see if we can make like an automated like plant like vegetable garden or something would be kind of fun. Like something actual like physical, like our own little computer system thing, rather than just software, right? I think getting into some more like hardware related topics would be kind of fun. Cool. Well, I really appreciate you guys being here and joining me for today. Let me give you a little preview actually of our project that I've been working on. So this is called Pocket Farm. And what it is basically like a online web app tool to make track your crops, your at-home garden. I do like to, I really liked my plant pathogen classes and my plant biology classes that I took. I did learn a lot from them about like cultivating and like in my biology classes, doing like tissue cultures and stuff. So I did have some experience like working with, plants and things like that because, you do learn a lot about plants as well as humans in my major. Kind of like all about like life in general. And I tie that into chemistry as well. And so I really enjoy actually, kind of farming and gardening, and it's pretty fun. And so I've been building this kind of web app to um, basically where you can have your own pocket farm, like basically like your own farm in your pocket to track your crops, right? Or like a not your own farm. It's not like you're making digital, not having like like digital crops or whatever, but you're just like logging like a log system for your actual physical crops in your whatever in your closet or whatnot. Um, so here at Tails, I made this little mascot guy. Well, I didn't make him. I did some old prompting. It took me some good time to get the art style right. I kind of want it to be like Adventure Time. I'm probably going to reach out to an actual artist to like, when I actually kind of launch the program to redraw these into like SVG vectors and then give me the actual like path objects so or whatever. Um, right? So I can, support actual artist creation as well as, get better quality images for our overall mascot here. But it's kind of funny. I think it was kind of a funny, like pun or whatever for our mascot to be kind of like this person that guides you through the site. It's kind of a cute, fun little mascot to give it like a good, like fun, like quirky little vibe or whatever. And his gardening, I thought it'd be kind of a really funny idea. His name is Pothead. It's really funny. It's like, because he just has a pot on his head. It's kind of ironic and kind of a funny pun. And so, anyways, it just kind of had these little cards I kind of whipped up. I was working on last night. So I worked on all this art yesterday, kind of getting the right prompts, and I had to go through and remove all the backgrounds and really fine up some of the line work on stuff in my Affinity in Photoshop and stuff. And then I made these cards to display them, some kind of like prompts to work through the site. Now, what I think I'm gonna do, this will be like my hero page. Now, the hero page will be, I think I'm gonna make these cards bigger, and then make a carousel, so that you can, that will like slide through these cards, automatically or whatever at the start here. And then there will be various buttons on each card to provide like link you to certain things would be super fun. So I think I'm going to probably replace maybe this one or add another card for like sharing like maybe like taking maybe do him have taking a picture of a crop and being like so you can like share it to your farm board or whatever, like because that's another thing I want to do is like you not only can track your at home garden, your closet garden or whatever, but you can also like share onto like a social board your grow, right, or your tomatoes or your cucumber whatever you're growing. You can share it with others, and they can see the exact like events that you did that took place. They can see like your statistics of the entire grow. Like I think it'd be really fun to do it that way. Now I just have to kind of work through some quirks on the back end. Well, obviously I'm kind of designing this front end, so honestly that's a lot of work, guys. Like doing design both on the front and back end. I wish I could just focus on one or the other and have and, but it's hard to do it all by yourself because you have to not only design the feature but then go in the back and fix it all up and tie it all together, which is really it's not that easy. So I yeah, so I have to figure out how I want to actually track the events. I think I want like you know various like data. I want to think like I kind of want it to be like pretty open ended. Like I want so I don't want it to be too difficult, but I don't want it to be too simple to where it's not enough information, right? But I want it to be simple enough to where it can be really simple or it can be difficult if you want it to be difficult. Now, this is what I mean. Like this is what I mean. Like if uh, if you only want to track like just when you watered, like just when you watered and the height, right? If that's all you wanted to track, you could just add in those two tracker statistics, right? Now, if what if you wanted to track like a bunch of them, like you wanted to track the height, you wanted to track the light, the humidity, the you know what you the fertilizer, the waterings, all these different things. Do I want to try to encapsulate each, like how do I want to record this data? That's the thing, right? Is that how do I want to record the data, because I need a way, I want to figure out the most like an optimized way to kind of tie it all together. Now I might be thinking about this too much, but I'm trying to be smart about it. So for example, let's say, now the thing is now it might get annoying though if you're as a user and you have to create an entry. Every time you go to create an entry, you have to add back in all of your statistics that you wanted to track, right? So maybe I it just sounds like a lot of work, honestly, and I have no idea how to do it. But like allowing the user to set like a template, save a template to their profile for what their events should look like every time that they go to create a new one. I don't know. What do you guys think? Because I also want to have like the events have like tags, right? Or like filter tags, kind of like Reddit or whatever, how they have tags. And these tags are like how these events are kind of tracked or whatnot. So now, the thing that would make that difficult is if I have an event that has two different things take place in it. So this would require the user to create an event for every single action that they did within that little like session on the plant, right? So like I'm just trying to think about like what would be the best way and the most user friendly way and what I think would be a fun way to do it. Well, like honestly, like I keep gravitating back to kind of that. I keep gravitating back to just kind of a blank slate every single time, because what if you don't want to track height every single time? Like what if you just track it once a week, but you do feedings every 3 days and you have to make those events, right? So by having like a 0 or NA in for the height track or whatever other the template trackers that you did, like it it wouldn't make much sense. So I'm thinking, now that I'm talking, thinking this through, what we'll do is we'll probably have, okay, let's create an event. It opens up like the event kind of forum, like it brings that to the screen and says, okay, let's go ahead and jot in some information like, use today's date or use a custom date, right? Like a switch. That's something we need. You have the date and time, right? Optional time if you want to add the time. Um, you would want to, and then potentially just like a repeatable component with a drop down for all of the different things that you can record, right? And then once you select one, it allows you for the ability to create another one and another one and another one for additional statistics that you would like to track in the event. That could work. Hmm. What's going on, Prawn? How's it going? But what do you guys think about our little infographic cards that I whipped up last night? I think that they look really nice. I worked hard on them. I like them a lot. Let me actually, I'm gonna see what they look like without the border. So let's go to this and do our info card here. And let's take off this border. It's definitely like kind of cute, right? So then what if we do like we made the background of these guys white so that they kind of pop off the screen a little bit more. Maybe we won't make it white. We'll make it like a little bit of an off-white. A little bit whiter. Honestly, the green doesn't really look that bad either. Kind of like honestly, that doesn't really look that bad. Kind of like our default colors. I kind of like it actually. Let me go to my nav bar and grab my color of my text here. This is my main color. Let's grab and throw it here. Yeah, that doesn't look that bad. Right. It's just the same color as his shirt, right? So what if we maybe made this a little bit darker? Or maybe let's go back and then make this go darker. Or this is transparency, right? What if we just did like a light green like this? That's kind of cool. What do you guys think? Should we just do white? Maybe like more of like a cream. Yeah, like this. Yeah, like this. A little bit lighter. Right there. Yeah, that looks pretty good. Nice complementary colors going on with a little bit of dark, light in the background, dark. Usually it's kind of dark to light is kind of the vibe that usually goes, right? But thought about taking the boot.dev classes and streaming through all of their stuff. Are you asking if I thought about that or oh, you're just asking if you do it? Yeah, that sounds like a great idea. I kind of watched about like the first hour of the TJ do the memory on C. I got some exposure to that, and then we're obviously going to dive into the book. Maybe a little bit lighter. Yeah, I like that. Yeah, that looks nice. Okay, let's see here. In like 15 minutes, can we whip up a potential can we whip up potential? So this is what we're doing here. We have our data that we're just mapping into info cards here, right? Okay, then can I go ahead and let's do need a okay, so this is the div that they're in, right? Okay, now let's do. There was this thing I was watching last night. Let's see if I can find it. Care. Yeah.
So,
Okay. Let me see here. Okay, so let's go ahead and create a new component here called photo carousel.jsx. Let's take a little kind of dummy one here. Go into photo carousel, add this. Cool. Let's go ahead and do photo carousel. We're gonna have this is gonna be images, right? Cool. All right, let's take this. Let's open up a div. And then, how do I want to do this? Also, the export default function. Hold on, sorry. Okay. So we're open up this div. We're going to do a class name of overflow x, overflow hidden. Then we're going to do relative, right? We're then going to do another div. And we're going to do in here a class name equal to flex. And inside of this div, hold on. Do images, right? And we're going to do class name of flex. Okay. And then we're going to do, another div. This is going to do, we're going to have a button in here. Open this up. Let's go open up our React icons. Arrow. We want this guy. And then we want the arrow left.
You're not that guy, pal. Trust me.
Hey,
You're not that
who's
guy.
that?
Okay. Okay. You? Absolutely.
Extreme. Thanks so much for following along, dude. Appreciate you so much joining me. Okay, so we'll do that, and then um, so in the button is going to be the FA arrow left, right? And then let's do this really quickly. Let's go to app.jsx. Let me import photo carousel. We'll take our photo carousel. I'm gonna throw it into here. Ah, come on. Okay, nice. Okay, so now we can see it going on here. Now what we'll do is we have this button. Let's do class name rounded full. Let me go here, duplicate this down to arrow right, border. So these are going to be, this is going to be if I between yeah. Hey GKKG, how's it going? Okay, so then we're gonna do. I'm just gonna delete this one really quick and work with this one for now. So we're gonna do heading 1 rounded full. Shadow. Let's see here, what else kind of shadow? I'm kind of following this guy. He had a really nice one I liked. Wanted to see what he had. So he just added shadow. He said BG white. Text gray. 800. Hover. Yeah, we'll do gray 100. No, gray 50. They're red. Yeah, okay, so let's do nice. Then let's do really quickly also here a okay, that's fine. Let me maybe make it a different arrow. What about like This is the left. Let's grab the right. Okay, we'll throw the left side. Okay, here we go. And we'll go cursor pointer. Nice. Okay, cool. So let me go to our app here. No images is equal to, I'll have to put in something here. So then let me ask really quickly. I'm gonna take this. Go. Yeah, here we go. Need to ask it a question here. How to make this map a list to feed as a prop to the photo carousel. They're not images, they're components technically. Wait, I'm not following this. If the map stores component functions. Slides. So let me take this. Card data to map all of these. Right. Slides. There we go. Okay. So now Why am I not getting these images? Huh. So you do images.map component index into a div. It's not going into here. Right? Inside of this div here, instead of the images, I'm gonna paste this. Images.map for every slide. There we go. Okay. Cool. No, we already finished doing the C stuff earlier. Working on something else here. Cool. Okay, let's keep going here. Let's see what we can do. I want to try to build this carousel. So we have this. Buttons. Between 4. It says 0. Flex. nice. Put it right on there. Really transparent. Oh, nice. Oh, cool. That's cool. Okay, so then we're gonna have to import.
You're not that guy, pal.
Oh,
Trust
thank
me.
you.
You're not that guy. Okay. Yeah, you?
Let's import
Absolutely.
state. Who's that? Who was that? Hey, Rhino, thanks so much for the sub on YouTube. Extreme Kinetics, thank you so much for the sub. Appreciate you guys so much for joining me. Welcome, welcome. Okay, so we're gonna have this use state, right? And then in our export, we're gonna have a variable const current and set current. We're gonna equal to use state with a default of 0. Okay, then we have this. Then we have this const previous is equal to a function, arrow function. We're going to set current to the current, and then current okay, and then you have const next, which is equal to
You're not that guy, pal. Trust me. You're not that guy. Okay. Yeah, you?
Hey, who's that?
Absolutely.
Who is that? Sidar, thank you so much for the sub. I appreciate you so much joining me. You're awesome. Welcome. How are you doing? Let me know more about you guys if you guys are here. I appreciate you guys being here. Welcome. So then we have, which is equal to this, which is current equal to slides dot length. Ooh, sorry. Images dot length less than 1, then 0, else current minus 1, like so. Right. I think I have to give this a class name with I have to do with this guy. But then the photo carousel itself, overflow hidden relative. How do I get the images to go on top of one another?
Also make it relative so that we can
Huh. How do you... Why won't these go by? Why are these images not stacking? Flex column. So I just need to map them into my own div. Yeah, okay. Perfect. Okay, so then if we add in button, right. Why is this? Oh, look at this. Yeah. What's going on here? I really don't know what's going on here. I'm bad at JavaScript. So this becomes this. But now it's this. Just get rid of this. Oh. Where is this border coming from? Where this? It's coming from this. Guy. Dog's growling. Here. Why am I getting that? Why am I getting that? What is going on? What's going on? What the heck? What is this? Is there a shadow somewhere? It's this, but it's this guy. No. What is that? I go here in a border. Oh, I don't know. I have no idea. No idea. So confused. It's definitely this. What? Slide to div. Oh, that might have did it right there. No. All the images in there. This is where all the images are. It's in here. Do a border here. Let's run everything. It's not making any sense. There we go. Now we need to do flex. Column. Okay, so now it's just that the images aren't Doesn't make any sense. I'm so confused. JavaScript is like my, or this stuff's like my enemy, dude. I'm so bad at it. I take this. I don't see anything. Doesn't make any sense. Nice. I'm so bad at this, dude. There we go. Okay, cool. Go to carousel. Let me go to my info card. Let me make this 800 pixels. Oh. Nice. That looks really good. Okay, so what we'll do. Nice. Appreciate that, Ray. You always got my back. All right, guys, I'm going to wrap it up here. Thank you guys so much for being here and joining me. I appreciate you guys so much. You guys have a great day, and I'll see you guys tomorrow.